welcome to After Hours Engineering. We've come to the point where our hack job of an assembler is starting to push its luck. To continue using it would require a really big overhaul, which is not really within the realm of the series. So instead, we're going to switch to a professional grade assembler, Gass. So let's go. It all begins by installing the Toolchain, and for us, that's going to be the RV32i and RV64i Toolchain, and we can do that via the GCC RISC Toolchain. For us, we'll get the sudo app installed. That'll install the multi-lib for us. Now, I happen to know that, and I'll show in a second what that is. But the second way that you can install it, and there are several ways you can do it, is using the GitHub account for the toolchain itself, the RISC-V compiler toolchain. And once you've cloned it, you go through and install any of these tools that you may need. You may not have them. And then eventually you'll come down to choices that you can make. You can either do the new lib, the Linux one, but I'm going to do the multi-lib one because that'll give me the 32-bit and 64-bit compiler and assembler, but I'm mostly interested in the assembler. Now, once you've done that and you've installed it, you'll really need to know what it is that you've installed. You need to be confident in what you have, and the easiest way to do that is to talk to the linker and grep out the word elf. And in it, it'll show you the targets and emulations. And what you're looking for is ELF64 and ELF32. If you've got that, then you're good. You've got both targets and you're ready to go. You're now ready to begin assembling and setting it up. But the question is where does the GNU toolchain come into? So let's take a look at the diagram here. Now in this, the assembler toolchain, we just installed it, comes actually in three most important roles for us: the assembler, the linker, and the object dumper. Now the object dumper is optional. So we start up here with our source code. That's our glorious program that we've written. It goes through the assembler and out pops an object file. Now we may have added some symbol references in here, and some of them are going to be defined optionally in a linker script, and they're combined together by the linker, so it'll try to resolve all the symbols that you have, and it'll complain when you're using a symbol it isn't able to resolve. That happens with the LD program, or the loader. Its historical name is called a loader, but it's thought of as a linker. It'll produce a executable, and we'll take that and pass it to the object dump. Now here is a choice that I made. Typically you might read an ELF file directly, the executable, but we're going to go ahead and use the object dump to produce a text file. And that text file will be very similar to our assembler in that it lays out for every line an address and an instruction. Now the difference is that the output from object dump is in byte addressing form. Remember, RISC-V is a byte addressable processor, so that's what it produces. However, readmem is expecting the word addressing format. So we're going to pass it through a shell script that'll extract only the instructions out of it and then convert it to word addressing into a hex file so that then we can load it into Gassssss and begin embedding it into our bit stream, which then loads it into the FPGA. So overall, this is our goal right here. We've got the yellow boxes installed. That's what we just did, which gave us our assembler, our linker, and our object dump. And now we're ready to start working with the monitor right here. The monitor is the beginning of our journey here, and we have our little character. His goal is to make it through the maze and out into the free world of Verilog. The monitor program that you're about to see isn't a complete monitor program. It's actually a replication of the previous episode, but done in GNU assembly so that we understand what's going on without having to look at new code. So let's take a look at that code. So it's in GNU assembly, which means it's following the standards of most assemblers. We have directives inside of here, and this defines constants. So we have our port that we have for the offset in each particular register. We'll see below different control sizes, register addresses, masking flags that we've seen in the previous one where we were looking at receiver and the transmitter. Find some constants here as well. The end of transmission, which is Control C, character turn and line feeds, and then all assembler files are broken up into sections, and the very first section we're going to define is where our code goes, which is the text section, and we're going to force it to be aligned to a word. Even though we're not using compressed instructions, the Femto only looks the lower 2 bytes. We define the start or entry point here using the global directive, and here's where it starts. Now this code looks similar to the original monitor, but it's almost identical. Here we're loading in the address of where the ROM data is, or where our constants are defined, and then we turn around and we go to that memory location based off of an offset and load it into S2. That'll give us the base of port A, which we've seen before, and the UART base as well, and that one's loaded in. And then we load in the stack bottom. This is a symbol right here. This is the start symbol. And symbols in the assembler are literally just address numbers. They're locations. That's all they are. It's different than in a programming language where you'll have a variable defined that holds a value. These are symbols, and they are strictly just addresses. So this is a symbol and this is a symbol, and we'll see where those are defined in a moment. So we come down here, we load just like before. When our thing boots up, it prints out an OK, and we clear out the LED display. Then we begin polling, waiting for a byte to come in. That's using the jump and address link. We've seen that one. One thing you'll notice in here so far is that there are some pseudo instructions. GNU Assembler supports pseudo instructions, or as it calls them, aliases, and we're actually using those, and we'll see in a minute what is actually generated with these pseudo instructions. This is not an pseudo instruction. This is the actual JAL jump and link. This is a pseudo one, load immediate into A0. We come down here, we're taking and reading the received byte because we just came out of the polling. We're grabbing it, putting it in T0, copying it, writing it, echoing it to the port, and then echoing it back to the terminal so that we can see what we're typing. Then we check for, there are 2 different things, the end of text, which is a Control-C, then we go to exit. Otherwise, we look for a carriage return. If we didn't get that, then we jump 1 forward. Now here's something for the assembler, is it supports local reference labels so that you don't have your code sprinkled with all kinds of esoteric looping values. Instead, you can actually move forward or backwards in increments based on numbers. So I've got a number. If you put a number here as a symbol, or a label in this case, you can actually move forward 1, and it will move all the way to this one. If you had another 1 down here, you could put 2F, and it wouldn't jump to this one. It wouldn't jump to another one symbol. So I'm using those as locals. Otherwise, I would have had to put some simple like continue label here and then say jump to continue. Then if it isn't any of those, we move forward 1 symbol and we go back to scan input up here. And this loop goes around and around. We've seen that again in the previous code. Otherwise, if they gave us the end of text or the Control-C, we jump down here, print by, and leave. And then we have all of our other subroutines down here, the poll, text busy, which is we're reading the control register. Those were those constants defined, and we're applying a mask and going around. Same thing for receive. We're reading a different value and masking it with a different value. We're writing to port A. Here's where we're printing a string, and you'll notice I've added stacking capabilities to this one because this particular method might be called within another method, but in this case it's not. However, this subroutine is calling another method, and we're using the jump and link instruction, which potentially will change the return address. So we back it up first, then we make our call, and then when we return from this, we continue. So while we're in this tight loop, now here's the backwards version of the forward one. So I've gotten a label here. You'll notice I have 2 1s here, but the jump 1 backwards will take us to this label 1, and this one will take us 1 label forward, so it'll go to this one. So it just, again, is saving us from creating almost meaningless symbols here when all we're trying to do is move locally. Print character, which is doing all of its stuff. And then we have our another section defined, and this is generally where your read-only data is. Now right now, our SoC only has BRAM, so all of it's read, write, and executable. But I'm just being formal in this case. I'm setting us up for when we get into, say, flash and static RAM. Again, we want it aligned, so we force alignment to begin here. And here's the base address of the port and the base address of the UART. And then we have a couple of strings that are given their own symbols for address ofs. And now you'll notice that I have both an alignment before and an alignment after this. And what this is doing is and we'll see in a minute in the output, is it's forcing this text here to be aligned within its own address space. And it makes it much easier to work with. If I took this carriage return out, we'll demonstrate this, you'll see that it isn't aligned correctly. And then finally I have the last section defined, which is the stack. And I've set it for read in, write, and no bits. And then again, I force it to be aligned, so no matter what this stuff is coming out up here, we'll force it to be back in alignment. And that's it. That's the GNU assembler, and that's the source. Now we can move our character along our path. We've just used the assembler, and we'll have an output here. And now we're at the linker right here. So let's take a look at what a linker script is for. Bring up the source again, and we'll come over to our linker. So this is a very, very, very basic linker script. If you really want to see a full-fledged linker script, all you have to do is pass the verbose flag to the linker, and it will spit out the default script that it actually uses in order to produce something if you don't give it a linker script. However, in our case, we do want a linker script, and this is the basics of it. We can give it an optional output architecture. It'll figure it out by looking at the code, the object file. We can give it a start point, and that's some semi-optional depending on what your code is doing. The default is start, so I don't really need to give it the entry macro here. And then next is a memory. This is optional as well. Just about everything in here is optional except for sections. So for memory, granted we are only dealing with block RAM, and all of it is read, write, and executable. I've done this in order to set us up for future episodes where we will need to define the memory layout in terms of static RAM, which is on the Schoko, the flash that's on the board, and some of them will be BRAM or ROM and a stack, different places. So for me, just to practice a little bit, I've set up a BRAM at 0 with a length of 256 bytes. The ROM follows right after it with 256 bytes, and then a stack after that. Now that we have our memory locations defined, we can assign them to different sections listed in the sections area. And the format of this is a bit more complicated, but I'm using the simple format, which simply says, hey, go to this memory definition here and use its origin and its length to define this section right here. So basically I'm saying that for all text sections, and literally all of them coming in from all of the different source files, if you only had one source file, which we do, you wouldn't need the asterisk right here. But if you are dealing with multiple text files, you will need to say, hey, take all the text sections from all of your .s files and put them in this section right here. And the same thing for any other sections you have, like read-only data. Now here, I'm defining a symbol, an address, and the dot inside of the linker indicates the current location of it. So as the linker is going through here, it's assigning this dot different address values as it moves from top to bottom here. The dot is going to represent the bottom end of BRAM or the top end of the ROM defined up here. So the dot is actually location 100. And I've defined that. Now again, this is a symbol that we referenced. You saw this inside of our monitor code here. So if I come back up here to ROM data right here, you can see that it wasn't defined inside of the monitor, but we did define it inside of the linker, which means we can see it in the monitor when it comes time to resolving that symbol. And the same thing for the stack bottom as well. So I've set up 3 different sections with 3 different names, and this stack here is referenced inside of the monitor. If we scroll back down to the bottom, you can see here is the stack section, and I've labeled it as read write and then no bits. And that's what you have. So now that we have our linker and we've defined a few symbols in it, we can now go to the next step, which is to run the linker itself. Okay, so we've created our linker script and our source file. We're now ready to move on to the object dump. The linker just run and it's produced an executable, and so now we're going to run the object dump command. And it in turn is going to provide this firmware output in byte addressable format. So let's take a look at the firmware and what it did. Come over here to code and we will show the output of the object dump right here. So when you run the linker, it's going to go through and tell you all about the sections that you created. It'll tell you what format, excellent, 32 bits, so it recognized that we were 32 bits. And it dumps out something very similar to what my assembler did, but using pseudocodes and actual symbols and starts. So here it is. We've seen this kind of before with mine, but notice that it is in byte addressable format right here. These are in bytes, so 0, 4, 8, C. Those are counting in one word increments, but in byte addressable form. So there it is. We've got all of our stuff. We can see it's created all of our symbols. These are all symbols, so they have an address associated with them. Here's our ROM data. There's its address. The strings that we had defined in here, there's the data that's at those locations. And here's the stack at the bottom. So this is what the linker will produce based off of both our source file and the linker script. Okay, so now that we have our output in byte address form, we need to convert it into a format that's commensurate for loading it in and embedding it within my bit stream. So in order to do that, we're going to create a very super simple little Go program that reads out these instructions that we saw and puts them into a hex file in word address format. So let's take a look at the code here real quick. Here's the main code right here, and over here is the out file that we're going to read. And you've seen this format with my assembler. It generates code and addresses and the instructions that we used in it. Over here to the left is the super simple scanner that we used. So in order to read this, it's really easy to just write a regular expression to identify this right here and nothing else in the file. So we'll take a look at that real quick. So this is the regular expression. Here's the same file. And you can see that this regular expression is identifying the exact pattern that we need. And we'll get it in two groups. We'll get the address and then the instructions. So no matter what we click on, we get the address and then the instruction. So it just simply goes around the scanner, trying to locate the instruction itself. And when it finds it, it converts it from byte address into word address by dividing by 4 and then writing that to the hex file. So if we take a look at the hex file, that's what we were just looking at. You can see that that's exactly what it did. It spit it back out with the word address form and all the instructions. That's it. That now we have it in a form that's commensurate for loading into a bit stream. Now that our character has made it all the way around the diagram, we're ready to take a look at what orchestrates all of this and puts it together into a workflow. For that, we'll need to look at the make file. So we'll pop that down. At the top, we have our RISC-V toolchain. And again, depends on how you installed it as to where it is. In my case, I compiled the entire thing, so it sits here in op RISC-V. But if we look at the terminal, you can see that if you did it through a package manager, it probably ends up in user bin, and then you don't even need to specify the path. But in my case, I compiled it, and it sits all within the opt RISC-V bin folder. And you can see that it compiled everything, and all that we need is the assembler, the linker, and the object dump command, and that's it. There's the linker. And at the top, you can see we have our gas, the linker, the dump control. We have the name of the module. These are typical things we've always seen in my type of make files. It gets dumped to the RAM disk. The default here is to run the assembler, then link it, then dump it, and then convert it into a hex file. So to run gas, remember over here in our processor, the Femto, it was telling us what architecture and ABI to use. Well, I've added that to the assembler, and I've gone ahead and told it the default, which is little endian. I didn't really need to specify this. I'm just being explicit. I don't want the assembler to try to do any kind of optimizations. I want it to just output straight up whatever I type in, it comes out. And then I don't want any architecture attributes. It just clutters up the file that it doesn't provide anything. And then I do not want position independent right now. It really doesn't matter because this is all one single file, and I'm not dynamically loading anything or doing any of those, or repositioning the code. Later on, when we get to the point where we're running a monitor and we want to upload a program, we want to upload it somewhere. And we can either hard code that address or compile or assemble it in position independent code. For now, we're no pick. Then we run the linker, and I do have to tell it what emulation that I want. If I don't tell it this, the compiler GCC could choose to actually run the assembler via GCC, and it will notice that you have a .s file and trigger the assembler itself. But it'll also trigger the linker and provide the appropriate emulation that matches. And that's what I'm doing here. I'm providing the emulation. Now, how do we know what emulations they are? If we look at the linker's output, we can see that if you ask for help on it, and I've routed it to a text file, it tells us all the supported emulations that it does. And again, we're running a multi-lib version of the assembler, so it's going to have not only the 64-bit, but it'll have the 32-bit versions. And right there is the one that we are interested in ourselves, is this one. So with that, we know we want an output and we want a map file. The map file is just informational. We'll take a look at that right here. And what it does is it tells us confidently what the linker script has built for us. We wanted our RAM at BRAM at 0, the ROM at 100, and the stack at 200. Everything else is nice. It gives us a bunch of breakdowns on the sections within it, but it's not. The map is kind of useful depending on what you're doing. And then we tell it we want the script that we're going to use, which is the LD script that we've already looked at. So we're telling it to use this script right there. And then finally we come down and we run the dumping tool with a bunch of parameters to help format it for us, such that width 4 here tells us how wide this section is right here. We don't want that. I'm being very explicit as to what sections I want it to appear in here. Typically, you don't really need to specify this. It'll just come out. But I'm being very specific. I want the text, the data, the read-only, and the stack. And that, in turn, will generate the out file that you see over here to the right. And then finally, we need to convert this file, which is, again, in byte-addressed format, into this file right here. And we do that via the Go program that I showed you earlier. And then that's it. What we end up with is this nice hex file that we can then run our make tool for the FPGA and embed it in, just as we always have been doing with the handcrafted assembler that I wrote. Before we move on to synthesis, I want to double back for a moment and talk about alignment. You remember the section where I was talking about right here, where we had an alignment of 4 above and an alignment of 4 below? Well, let me take out this alignment, and over here to the right is the output. And I'll run the make file one more time and take a look at it. So I'll come over here to the make file. You can't see what I'm doing. And I'm going to run make, and we can see that the string by is still aligned to 4-byte alignments, which is great. But if I take the R out, the carriage return, it will fall out of alignment. So I'll hit make again, and now you can see assembler, what it tries to do is compact the number of bytes. That's what it wants to do, and it's the best way to do it. But for me and my simple approach of dumping these out, I would have to do more work in order to expand this out. So it's not exactly helping me. So the way to do this would be to add in the alignment. So if I do this, copy this down, save it, and then run it, you'll see that the alignment is back. So this works for my assembler. However, it just so happens that when I put the carriage return in there, that happens to automatically align it, and I don't need that. But I'm leaving it in there to remind me that I really need this word lined up like this so that when I run my hex converter, that it properly reads 4 bytes at a time on a line. You typically wouldn't want to do this if you're compiling, because this actually expands the code out and you're wasting 2 bytes. Okay, so now we're ready to synthesize. First, we'll build our firmware. So we'll come over here, run make. There it is, it's been built. We'll then come over here and we'll start up our terminal program, which I'm going to use screen this time. There it is, it's up and running. And then I'm going to come over and actually take that firmware, embed it in, and upload it just like we did before in the previous episode. So I'll get that started here. There it goes, it just uploaded it. And so now the green light on the Schoko is green, and we're now looking at the word OK on the top here. Now we can start typing. Now remember, in the Gas assembler we echo every character we type in the keyboard, so that's what we're seeing. We can hit return and type hello world. Backspaces don't work yet. Hello world, like that. And of course, if we hit Control C, which is end of text, it'll recognize that and put out the word buy. So excellent. We've now transitioned over to the gas assembler, and we're ready to start working on a true monitor. Excellent. With our newfound knowledge of gas and its workflow, we're ready to build a basic monitor, all while knowing that it is flawlessly perfect.